Hey guys, in this video we're going to be covering the basics of differential equations. I've elected for an example that isn't too difficult, but it isn't too easy at the same time, and I think if we walk through this one example, it should set you up for all the other types of questions that you might encounter, and at least give you a nice fundamental bit of revision as to how we approach these types of questions. Now, differential equations, kind of a new topic, but not really. If you guys noticed, half of the working out in differential equations is basically integration. And I think that's a really big thing to keep in mind. It's not that difficult of a topic, kind of just an extension of integration, which you learn before differential equations, right? So the example that we'll be going through today is dy, let's make sure it's in screen, dy on dx is 2x plus 2x squared, no, plus 2xy squared, and we need to solve this differential equation. Now, this is a differential equation because it includes, or it contains a derivative term, and they give us some conditions as well, which I'll just quickly get down. So they tell us when y equals to 1 for this function, y equals to 1 when x equals to square root pi on 2. So all of this information will help us solve for the final answer. Now, in order to start our differential equations, anytime you get a differential equations question, you want to basically set yourself up so that you can integrate the answer, right? You're trying to find, remember the goal is that you're trying to find a set of solutions that satisfies this equation. What kind of function, y equals to something x, can I sub into this differential equation so that it satisfies both sides? Or in other words, what derivative or what function, when I differentiate it one time according to x or with respect to x, would I produce this function 2x plus 2xy squared, right? So which function has this kind of derivative? In order to do so, we need to integrate to find the primitive, right? But like an integration, or unlike an integration, sorry, every time you're given a question there, it's already set up so that you could just immediately integrate and follow through the rules of integration. In this case, you just need to do the setting up yourself. So clearly, I can't actually, the equation isn't in any form to be integrated, but what I can do in this case, and this is I feel like this is the most important part of differential equations. Once you overcome this hurdle, every other question is basically the same thing, but kind of like a bit longer maybe, or they try to trick you by placing it inside a really long question and kind of obscure the information. But at the end of the day, the technical skill required is just this. You need to separate the derivative terms. You need to separate the variables so that they are on each side, kind of like on their respective sides. Let's keep it at that, yeah? So what I want to do is, since dy is already in the numerator on the left-hand side, I'll leave dy on that side, and I'll make that side kind of like my y side, right? Meaning all y terms should return to the left-hand side. Anything else should kind of go on the other side. And this is what they call in your textbooks the method of or the separation of variables method, right? We have, so dy, and since, remember, we want to keep dy on the left-hand side, anything y stays over there. Anything that isn't y goes into the other side. So I have 2x plus 2xy squared. And we have here dx. Now the thing is, I need to bring anything that is y onto the left-hand side, or keep everything that isn't y on the right-hand side. I have a y here. I don't want it to be there. So the best thing to do here is just to separate or factorize your x out. In this case, there's a common 2 as well, so I'll factorize that as well. And I'll have 1 plus y squared. And what you notice is I have managed to separate the expression so that they could be divided across. And now I can have all the terms on their respective sides. So you can see I have dy on 1 plus y squared, basically dividing over this term. And I have 2x dx, right? And with that being said, I think this is very close to what you're used to in integration, right? If I now integrate from both sides, you know what? I can actually just throw the integration signs onto here, right? So you can see on the left-hand side, you're integrating some function, 1 over 1 plus y squared, with respect to y, dy. And on the right-hand side, you're just integrating 2x with respect to x. And I think that is something we're all quite familiar with at this point. So we should have the left-hand side, you're going to end up with tan inverse. If you just check your reference sheet, that should be a pretty easy integration. tan inverse of y plus c. Now just notice, I'm going to call this C1 just for now. This is not something that you're going to do every single time, but since we're going through a bit of revision here, I'll leave it as C1. On the right hand side, you're going to have 2x squared all over 2. And obviously, we always add constants, right? C2. Now, there are two constants. Just to make it, I guess, just to follow the rules that you learn in integration, anytime you integrate, you need a plus c. And that makes sense. In this case, though, we can generalize these terms. And a lot of times in your textbooks, they won't even kind of, they'll just brush over these steps. Well, the 2's cancel out, don't they? They'll basically just brush over this, but they'll just have plus c. And in this case, the plus c represents the multiple c's that have been brought on both sides, right? So here, I could bring the c1 onto the other side, and you'd get something like c2 minus c1. Well, a constant minus another constant can just be generalized as a constant, right? So to save us all that hassle, we don't really say C1, C2. A lot of times when you're integrating both sides, you just have one C on one side, and it's sufficient to encompass both constants, yeah? Now, all I have to do here is basically, well, I kind of really solved the equation already. I've solved for the answer, right? This is kind of like our answer. It's not in the best form, but the thing is, I just want to quickly touch on this. What we've arrived at is what we consider a family of functions. So this family of functions would be able to satisfy the differential equation we started from the beginning, right? We call it a family of functions because we have this unknown constant, and this unknown constant says that there are multiple versions of this function that is able to fit into that differential equation. Luckily for us, if you're given some kind of initial set of conditions, you can use those set of conditions to actually find the exact function that will fit in there, right? So we'll sub everything in. Let's make sure I am in frame. We have everything here. Let's say tan inverse of y equals x squared. So we know that when y equals to 1, let's say we'll sub y equals to 1, comma, when x equals to square root pi on 2. Yeah. So you just need to sub this in and find out what your c corresponds to. So I'm going to have tan inverse of 1, which is pi on 4, right? Just some exact values there. Square root pi on 2 all together squared plus c. So this is pi on 4 equals to pi on 4 plus c. Oh, so luckily for us, our constant is actually just 0. That makes everything a lot nicer. Therefore, c equals 0. So really, our final answer in this case is just going to be tan inverse of y equals to x squared plus 0, or better yet, y equals to just tan of x squared. Oh, tan of x squared. And that's our final answer. This is the function that if I differentiate and if I substitute into this differential equation would satisfy both sides. It is our solution per se, right? And that's basically it.